Moderate intensity exercise. The main energy system used during moderate intensity exercise, such as a 400-meter sprint, is the anaerobic glycolysis system, or otherwise known as the lactic acid system. In this system, glycogen is broken down from the enzyme glycogen phosphorylase into glucose. The glucose is then converted into pyruvic acid from the enzyme phosphofructokinase. This system creates a total of 4 ATP energy, although only 2 ATP can be used for exercise. This system is used when the intensity is moderate and lasts for around 2 minutes. It is a good source of energy and can be used immediately. However, it cannot be used for a long time and creates waste products. The waste products that are created as a result of the ATP energy, when glycogen is broken down into glucose, then that is broken down into pyruvic acid. The pyruvic acid makes a waste product of hydrogen ions, as there is no oxygen. These hydrogen ions connect to lactate to form lactic acid. Lactic acid is acidic and causes an imbalance in the body which is not liked, which causes a burning sensation in the muscles, forcing the performer to slow down or stop exercising. The main energy sources in this type of exercise is a mix of both glucose and fats. At the start of moderate exercise, the main energy source will be glucose, by both types of energy systems, aerobic and anaerobic. However, as the exercise continues, this will allow more time for fats to be broken down into energy, and thus more work can be done, as there is a high yield of ATP from fats. Moderate intensity activity such as a 400-meter race requires ATP energy anaerobically for a longer period of time. The demands of a 400-meter sprint is usually quite high and requires a fair amount of power and muscular endurance. The start is a sprint at a high intensity and requires the ATP PC store. However, the energy system then changes to the lactic acid system or anaerobic glycolysis system. This system then produces overall 4 ATP energy, but only 2 ATP energy can be used as a result of breaking down glycogen into glucose, and then pyruvic acid, with different enzymes like phosphofructokinase. It provides ATP in a very short amount of time. However, as a waste product, it produces lactic acid. Lactic acid inhibits the release of glycolytic enzymes, forcing the body to fatigue, and starts to slow down so that the aerobic system can take over. The main energy source used during moderate intensity activity is fat. The respiratory exchange ratio during moderate intensity exercise is around 0.85, 50% of fat being used, and there is 50% of carbohydrates being used to make energy. This is because at a high intensity the RER would be around 0.9 to 1, and at submaximal exercise around 0.7. This is because at lighter intensities there is more oxygen being inhaled and used compared to carbon dioxide. However, when working at higher intensities there is no oxygen, and the method to create ATP energy is anaerobic, and the byproduct of muscle contractions is CO2. This is why there is an even distribution of fat and carbohydrates as an energy source during moderate intensity activity. There are several causes of fatigue when performing at moderate intensity and moderate duration. Firstly, fatigue can be caused by glucose and glycogen depletion. This is when the lactic acid system has been completed and glycogen has been converted to glucose through the enzyme phosphorylase. The rest of the process takes place and 2 ATP is made. This 2 ATP is used in the moderate intensity activity such as in a 400-meter sprint. This will occur nearer to the end of the race. The process to produce ATP anaerobically via the lactic acid system cannot be completed again unless there is a rest. Therefore, as a result of there being no glycogen or glucose in the muscles to carry on anaerobically working, this means there is a depletion of glucose and glycogen. There must be a rest of around 2 to 4 minutes to be able to recover this system, and can be a cause of fatigue. A second cause of fatigue in moderate intensity and moderate duration activity is lactic acid accumulation. During the process of glucose converting to pyruvic acid, this pyruvic acid can build up, and the pyruvic acid breaks down into lactic acid by the enzyme lactate dehydrogenase. The buildup of lactic acid inhibits the release of glycolytic enzymes like phosphofructokinase. This inhibition of enzymes leads to a high acidity which the body does not like. The body wants homeostasis, which is a balance in the body. Hydrogen ions, though, cause a decrease in the pH. The body then is forced to slow down from the pain that is caused in the muscles from the build-up of hydrogen ions. This is fatigue and occurs in the 400-meter sprint. The lactic acid will build up, causing them to slow down after about 150 to 200 meters. The effect that lactic acid accumulation has on the performer is slowing them down, and it also causes psychological fatigue, as the build-up of lactic acid can be quite painful, and the longer the performer withstands the lactic acid and carries on will mean that it will become worse. This can cause psychological fatigue, and the performer may choose to stop or slow down. Acidosis is the name given to an increase in acidity in the blood or muscles and occurs from lactic acid accumulation. Another cause of fatigue is hydrogen ion and pH accumulation. The hydrogen ions that are found in lactic acid is what the acidic part is. These hydrogen ions can cause electrical interferences with the signals in the muscles and nerves, which can lead to a slow energy reaction of glycolytic enzymes and impairs the muscle contractions. An accumulation of these hydrogen ions leads to the intense burning feeling in the muscles, making performers stop exercising and forces them to slow down. Basically what the lactic acid accumulation does. Although lactate is removed by the body naturally, and the body can also buffer this lactic acid, which weakens the effect, making it less painful and intense for the performers. The kidneys can produce hydrogen carbonate ions into the blood and helps to absorb lactic acid and form carbonic acid. This is then turned and formed into carbon dioxide and water, which are both taken out of the body and expelled from the lungs via diffusion and then exhalation. So, how can this fatigue be avoided? One way in which the fatigue of moderate intensity exercise can be avoided is by a process called soda loading, also known as bicarbonate loading. Some athletes attempt to drink sodium bicarbonate just before an event or exercise. The reason for doing so is to lower the pH dramatically just before the event, so that when in a 400-meter sprint, for example, when there is a large accumulation of hydrogen ions and lactic acid build-up, which will increase the acidity. The soda loading will therefore attempt to allow the performer to work for longer before the body's pH becomes very acidic, as it starts off very alkaline due to bicarbonate being very alkaline. It will shorten the length of time that the body will be acidic, meaning that the athlete can hopefully work for longer, as the pH will not become too acidic as fast. As you can see in the figure bottom right on the slide, it shows how training with soda loading can affect endurance training. During pre-training, there is not much difference when comparing the placebo with the soda loading athlete. However, once exercise begins, it is clear that the soda loading athlete is able to work for longer at around 1,200 seconds compared to 950 seconds for the placebo group. This shows that soda loading before an event can increase duration, and this is important for 400-meter sprinters, as it means they will be able to work for harder and longer, and therefore will get a better time. The bicarbonate group had a bigger improvement at 41% compared to that of the group taking the placebo. The placebo was a salt solution in this figure. Another way in which fatigue can be avoided is by a process called glucose ingestion. This is when the performer will ingest glucose just before an event. The purpose of doing so is to prolong the fatigue that occurs from the exercise. A performer will take sugars to spike the blood glucose, meaning that there is more energy. Here you can see an onset blood lactic accumulation graph, otherwise known as an OBLA graph. Here it shows the blood lactate whilst running at different speeds. At the start of the graph, you can see that a running speed of around 4 to 11 km per hour produces around 2 millimoles per litre of blood lactate. This tells us that the speed is working aerobically, as the intensity of the exercise is low. Therefore, oxygen can be consumed and converted into ATP energy from a process called aerobic glycolysis, by a Krebs cycle and so on. However, from the graph we can see that just above 11 km per hour, the lactic acid starts to kick in at about 11.8 km per hour, which is the lactic acid threshold, which is the starting point whereby the energy system changes, and ATP energy is produced via anaerobic exercise, and thus the lactic acid has started to be produced. You can see that as the running speed increases, so does the blood lactate. A reason for this is due to the demands of the exercise. As the speed increases, this increases the intensity of the exercise. And we know that a high intensity exercise or activity will result in anaerobic energy systems producing the ATP as it is available and doesn't take as long to produce ATP. It is immediate. So the lactic acid system will start to kick in after the lactic threshold, and as we know, a waste product of anaerobic glycolysis is lactic acid. As the length of time and intensity of the exercise increases, this will mean that lactic acid is going to build up. And the build-up of lactic acid results in the burning sensation in the muscles, which aches and makes the performer want to quit. Also, it inhibits the release of glycolytic enzymes, which attempts to force the body to work aerobically, and for EPOC to occur, which means that aerobic glycolysis can happen and produce energy and can return back to a pre-exercise state.